and things. Okay.
Rate of reaction and...
We're going to talk about 3 possibilities to start. 3 orders of reaction.
What's this called?
Method of initial rates.
Henry
Mark, we
Ross.
should worry about you, but I'm glad you're here. You can him up there.
It's so nice, Assassin. I have to turn my clothes backwards somehow.
Yeah.
What's that way?
It's paused.
Method of initial rates is what we're going to be talking about today. And
What's today's date?
it is the 21st. It's our phone. I've said
Seven.
Yeah, he was
Sorry, I'm sorry.
letting Meyer know, because I told him I'd let him know. He was coming in from the walkout. But he didn't know if that was class.
It is. He's welcome to be here, or you can make his own choices. Okay, so method of initial rates is a way of figuring out what the exponent is going to be. The rate of the reaction depends on the amount of chemical. Okay, X, well, I'll use their notation, say A for chemical and X for exponent. Okay, it depends on the amount of chemical. If you have more chemical, your rate is going to be faster. Okay, that should make sense. You put more stuff in the jar, it's going to react more frequently. Does it depend to what power on X? Okay, that for our purposes can be 0, 1, or 2. Okay? It could not depend on your chemical at all. It could be the chemical that you're putting in the jar doesn't affect the speed of the reaction. That would be 0th order. It could be first order, where it depends. If you double the amount of chemical, you double the speed. Or it could be second order. If you double the chemical, the speed gets 4 times as much. We're going to learn later on after HMC, like what's going on in the reaction to cause this. What we're going to learn today is how you find out experimentally which number it is. Let's talk about these 3 possible scenarios first. If it's 0th order, okay, reaction speed does not depend on concentration of chemical. 0th order means it's independent of that chemical. The number of dating couples at VMI, the Virginia Military Institute, is pretty much independent of the number of guys there. The guys could change by 100 or more, and it doesn't change. There's only like 27 girls and like 4,000 guys. So like the number of couples is completely limited by the number of girls there. The number of guys has no impact on it. Like if they change by 100 or more, right? So independent of one variable because it's completely dependent on the other variable. Come on in, have a seat up here, Maya.
What? I texted you.
In a chemical situation, this happens if like the reaction only happens on a particular like surface. It is limited by surface area. When stuff goes through a catalytic converter, which is like a thing that converts the waste that your car produces, has a limited surface area, and the reactions, like the 2 chemicals have to both bind to that surface where they can react with each other. Depending on how much of that surface you have is going to affect the rate of that reaction. So if you look at a 0th order reaction over time versus concentration, it's going to look like that. It's going to be linear, okay? As like the amount of chemical, like, as time goes on, you get more and more chemical, and it's steady and linear. If you look at the rate versus time, it's going to be flat. Okay? The rate will not change with time because the slope, as Henry noticed, is constant here. Mile and none. And this is change over time. It doesn't change. A first order reaction. It's physics.
It looks like derivative.
Like calculus with derivatives.
Yeah.
Like,
it is. There's an overlap there with those things. A first order reaction. Reaction speed depends on amount of chemical. It varies directly with your amount of chemical. Okay? This should make sense. Put in more chemical, the reaction gets faster in a fairly linear way. Okay? This is the sort of curve that we drew at the beginning of this quarter. You start out with 0. Initially it rises steeply and then sort of levels off.
What are the axes?
So this is concentration of chemical, molarity of chemical versus time. Okay? As the chemical gets used up, the speed that it's going to move at is going to decrease. Okay? My graph of the rate of reaction versus time is going to look like what? What's happening to the rate of the reaction? Is the reaction getting faster or slower as this goes
Slower,
on?
so it's
Getting
getting
slower.
down.
So our rate is going to decrease with time. Okay? As the reaction moves forward, this is going to be like decreasing over time until essentially this levels off. The rate is at 0. Smiling down. Okay. Our last possibility is second order. Okay. Rate equals concentration squared. I should put those in for the other ones where we have a 0 or a 1 or a 2 power. Rate varies with square of concentration. It is hard for us to, this is generally when it involves 2 of these molecules hitting each other. Okay? It doesn't just depend on one of them, it depends on both of them. They both need to be there for the collision. So the effects are doubled in terms of the effects. So our curve is going to be the same sort of shape, just more extreme. I don't know if I can draw it more extreme. It's getting more exponential, less linear. So that contrasts with maybe this, which is we just drew, and this, which is our first one. Okay? 0, first, and second. It is hard to draw it to show it to be more. Yeah, it's okay. There's not going to be a drawing portion on the AP exam. It's the idea of it's getting more exponential.
Just make it curvy.
Yeah. With this one, the rate. Sorry, I should put in my axes. This is time versus concentration.
We got it now.
Okay. This one is rate versus time. And this one is going to be curved itself. Okay? It starts off high and gets lower exponential, or in a curved manner. Those are our 3 possibilities. We're going to now look at various experiments that generate these possible scenarios. Okay? I'm going to pass out some pink pieces of paper. I have one that we're going to glue into our notebook, so we have one in our notebook as well.
Wow.
But I'm going to start off with these. Take one, pass down.
I don't think I forgot we had her as a teacher for like 4 years. Which was the last time we had her. Dave, you forgot.
So, here is some data. When I put it into the smartboard, don't worry about it. When I put it into the smartboard, it is not as clear, but you've got it here. We are trying to figure out this little equation here, where it pays it through. Okay? We are trying to solve for everything in here. Here is the rate data. Okay? We have these concentrations of the chemicals. When you first look at it, it's kind of a mess. Okay, we've got lots of like different things going on. What we want to do is isolate a variable. Okay, if I look at reaction scenario 1 versus reaction scenario 2, what our two possible independent variables are the amount of A and the amount of B. What did they change going from 1 to 2?
The amount of A.
The amount of A. What did they do to it?
Double.
They doubled it. Okay, so we can say that the concentration of A in trial 1 versus, actually I'm going to do trial 2 over concentration in trial 1. Put this down below where we're like solving for X. We are trying to find the exponent on this chemical A. So if we look at the concentration in 2 versus 1, and we look at the rate of 2 versus the rate of 1, okay, as you guys quickly noticed, this chemical was doubled. It's 0.02 versus 0.01. Let's look at the rates at this particular time. The rate in reaction 2 was 10.8 times 10 to the minus 7th or whatever it is. Okay, what is the rate in reaction 1? 5.4 times 10 to the 7th. Okay, if I divide 0.02 by 0.01, I get 2. If I divide 10.8 by 5.4, I get
2.
2 comes the resounding chorus of confident students. What is the exponent on this right here? This is what I'm going for, is this exponent x.
1.
Okay, it's first order because 2 to the 1 power is going to generate 2. So we have just determined that x must equal 1.
So that's just for.
That was just for the first. That was just for trial 1 and 2. Let's not jump to any conclusions here, Dave. Let's look at another time where A is the only thing changing and B is constant. Where's another reaction that does that?
2 and 3.
2 and 3. Okay, we can look at 2 and 3. Okay, so
Wait, B isn't constant. Oh, and 2, 3. Oh, yeah.
yeah, this is not changing there. So we can then say, all right, in this case, once again, it's 0.04 over 0.02 to the x power equals, in this case, it's 21.5 divided by 10.8. What's 21.5 divided by 10.8? Around 2. Alright, this is what, like 1.9 or something like that?
Yeah.
1.9 equals 0.4 divided by this. This is 2 to the x. 2 to what power equals basically 1.9? You guessed it, 1. Alright, so now we've got two pieces of evidence that make us feel like x is probably 1. You could do it again. Okay, we could put trial 3 over trial 1, 0.04 over 0.01 to the x power equals 21.5 over 5.04. This is 4, this is 4, x is 1. Smiling none? So normally it's going to be fairly consistent. Normally you don't do it 3 times. The first time we met this, so we went and checked all 3. Generally you'll just have to check 1 and you're going to see what's up. Alright, now let's hunt down for part B. Okay, for chemical B. Let's try and solve for its exponent, which is y. So what is an experiment in which B is changing but A is constant? 4 and 5. Right? If you look at 4 and 5, A is no longer being tweaked. B is the independent variable that's in action. Right?
Teachers and students. I know we had sort of a disruptive hour there, all in the name of a cause that students brought forth. If you are not currently on the walk, you absolutely need to be in class. We know who is on the walk, and so if you're not one of those people, then you have an unexcused absence. Teachers, if you can please take attendance right now, because all students who are not on the walk should be in class. You can mark them as unexcused, and we'll address the excused, unexcused issue afterwards. But if everyone can right now make sure that they take attendance, so we know exactly which students are in the building and which students are on the walk. We have a visual count of who those students are, but it would be really helpful if you took attendance so that we can know that. Thanks.
All right. Boom, boom, boom.
There you go.
Boom,
Just more minutes.
boom, boom, boom.
It's like half our class.
Yep.
Wait, what about
Oh,
blue?
hang on, I hear footsteps.
Blue already has an excused in there. Can't override.
Oh, I wasn't saying to override. I was just asking. I don't know why I was like
Why
that.
does it say male?
So great, the elementary school humor. All right, so if we look at our trials 4 and 5, okay, so again that's 0.02 over 0.01. Our rate of these reactions is 1.1 over 2.7. Is that correct?
Yeah.
Okay.
But it's
but
but
it's
2.7 times 10 to the negative 8.
Good. I was hoping something like that would come through for me. This is 10 to the negative 8. This is 10 to the negative 7. Otherwise, this is going to be confusing. So let's turn this into 1.1. This is 1 order of magnitude smaller, so I'm going to make that 0.27. Okay. So this works out, if you divide these, this is just straight up 2 to the y power equals, this is what, 4 point something?
4.07.
4.07.
When's lots of
Nope. What is y? That's
I need
right.
some logs for
Y
is 2.
equals 2. The effect of doubling this made the reaction 4 times faster. Smile and nod. That's what we are learning to do in this today. Like we've just done today's lesson. We're going to do it a couple more times, but that's essentially what we're doing. We're not done with these things yet. As you can see, once you have x and y, we can now write rate equals k times a to the first times b squared. That's where we are. We've done most of the heavy lifting. Okay? What is the overall order of this reaction? Is the sum of its coefficients. Okay? The overall order,
But I mean, K is to the first 2. Isn't it?
K is not a chemical that varies. That is a constant that we're about to solve for. So the overall order is 3. It's a third order reaction. Okay? Now, we want to solve for K. Alright? We want to solve for what the constant for this reaction is. Let's take a row of the reaction. I'll take row 1 and put the things I know in. The rate in this one is 5.4 times 10 to the minus 7. We're putting that in for the rate here. The K is what I do not know. My concentration of A is 0.010 molar. That I need to, oops, that's to the first power. Oh. Okay. This one that is 0.20 molar is squared. Alright, game on. Let's play some algebra games. Okay. So 5.4 times 10 to the minus 7 equals K times 0.01 times 0.04 is what that's going to be.
I got
0.00135.
Okay.
That's
Point 2 squared should be 0.04. I'm pretty confident about that.
Yes, it is.
Okay.
Times
And then-
0.01.
yeah.
Times 0.01, and then 5.4 times 10 to the minus 7 divided by all that. K equals
1.35 times 10 to the negative 3.
I used
0.00
135.
or 1.35 times 10 to the minus 3. Do we agree it's one of those two, which are in fact the same thing?
Really?
Okay. Alright, I'm going to take it one step further. If the concentration of A equals 0.3, this will stay the same order of magnitude and say 0.03, and the concentration of B equals 0.05, what will the rate of the reaction be? If I now know the K in the various orders, you can put this data into the equation we've just generated to predict what the speed of this reaction would be under any conditions.
0.0072. Or 7.2 times 10 to the negative 3.
Okay, so rate equals 1.35 times 10 to the minus third times 0.03 times 0.05 squared. You are punching that stuff through. You are comparing your stuff with the person next to you.
Oh, wait, never mind. No, take my answer for that.
Yeah, what was that second?
Wow, thanks, Henry.
Love and community, Henry. One sarcastic comment at a time. Someday you're going to learn to talk to girls. Not yet, not yet. Just wait.
I loved your lava comment yesterday, Dave.
Which one was the lava comment?
Yeah, right after I left in class.
Wait, where are we getting the
What was
numbers?
lava comment? I don't even remember.
When I asked you about the lava on the ring.
Oh, is this,
Oh. The Hoffman.
which problem is? Oh, this is an extra problem.
Yeah.
This is just, I'm saying, like, we can now work
What'd you
from
get
any
for that?
condition. Okay, so we're putting in these numbers here.
Me. That wrong.
You're comparing to the person next to you, the number that you got matches, and then we share, what is it?
No.
1.0125 that.
Which is in the same order of magnitude as some of the numbers on here, yes? Okay, so
Did you
matches, stuff makes sense. Alright, let's do the next one in your notebooks. Here, I'm going to pass out these little things you guys can use. Here, take one. Put that in your notebook. I'll see if I can find some glue sticks for you guys. Okay, so you want to have one of these in your notes in case the piece of paper doesn't fit.
Yes, Elliot, it is the devil's screw.
There's one. Mark and Henry, there you go. Alright, put that in your notebook.
No, remember Rachel's class?
Remember
Rachel's
Michelle's
class.
class?
Every day.
We glued so much in that class. Like,
I remember
we were
hearing about that when I was at WNL. Some WNL teachers came and like, wow, they do this thing where they like glue things in
glue
notebooks.
everything.
And they were like really impressed.
Why not use a binder? I don't know.
She
a little bit
did
too
me on
long.
the first day.
I mean,
There's
like,
scissors here.
Remember that?
I'll fold it.
She did me on the first day.
Oh, yeah.
Oh.
It's really satisfying though.
Oh yeah.
It is satisfying,
I think
but
wow.
I used to do the lick and rip next.
I remember like, it was like, okay guys.
Who's not using
like,
it?
some, like, where are the names? Things like match them together. And I was like, why are we doing this? This is so pointless.
Mark and Henry, if you're done with yours, you pass it this way.
how much should I put it on a new page?
This is the sort of problem you're doing. You'll see how much of that space it takes.
I'm not gonna burn to actually do anything.
Even if
You know, we go to the page there.
Oh, got it.
She used to tell us about how lollipops were the source of all evil in the world.
What are you on about? Oh, Michelle, yeah. She
Michelle.
hated lollipops.
You go someplace else, Mark?
True was in my
Who'd you
I do
have?
not have Michelle.
No,
I'm in
me,
the-
Trey,
I'm
who
in
is
the-
Michelle?
Michelle was our
Stop.
algebra teacher.
Michelle's the best teacher in the world.
So, right now, you and the person next to you are looking at this reaction, okay, and trying to determine the exponents x and y.
No, ours is that.
Dave
now,
just
you
gave it to us.
understand?
We're finding what?
Finding x and y.
Go sarcasm.
I said why? Oh, yes.
What's that? Satiric.
Yeah.
Oh, satiric humor.
Oh. Okay.
Yeah, I changed the background to a picture of like
Okay.
close to things.
J and J, figure out x and y.
One half equals 1.44. Okay. That's a 2.
When we do this in lab, the numbers are going to be much worse than this. In terms of not being like perfectly mathematical.
So,
Sorry.
how do you measure the initial concentration?
molarity stuff you put in the jar. That's easy to measure. The rate is a little more mysterious. That's what we're going to work on in the lab tomorrow.
Okay.
What's one? Two equals one. No, that's y equals one. 2 to the 0 equals 1.
Did you
Y
figure
equals 0.
The equation.
Should we do k now? Yeah, 2k. Overall order is 2.
7. 1.
So you're agreeing with the person next to you, and now we're just sort of checking in as a class, because we're starting to continue with this. Rate
Just 1. 0.
equals K times concentration of A.
You can tell that by looking at it. When
Mark
you
and
see
Henry,
that
what did you guys get
as
for the value for
stays
A?
the same and this changes.
I see the chart,
sign.
it's not mathematically
X equals 2. Smile and nod. Other groups have a similar thing.
0.04
Okay.
equals.
What do you ladies get for the concentration of the coefficient on B?
raise this to
0.
the 1 power.
That is the exponent.
And like
The exponent notation. As you can see, when they change the chemical, when A stays the same and B changes, it has no effect on the rate. The rate stays the same the whole time. So as you are tweaking that, that has 0 effect. That's an exponent of 0. Okay. Diego and Jack, do you guys have a K value for us yet for this reaction? 3.0054.
No.
No. 0.0054, 5.4 times 7 minus 3. Agreement on that? Groups are
Yes.
smiling, shaking, nodding. Alright. One other, whatever that is, smiling, nodding. Okay, so, one thing we have not talked about yet. What are the units on a rate of a chemical reaction?
Meters per
moles per
Meters
second.
Meters per second.
Per second. What is, it's not exactly moles, it's molarity. What are the units on molarity itself?
Moles per
Moles
liter.
per
So it's
liter.
moles per liter
Per second.
per second, which gets kind of confusing.
Or moles
Okay.
per liter.
Moles per liter second. Okay. Liters and seconds are both in the denominator there. I'm going to go back a sec and just talk about it as molarity per second. Alright? What are the units on these things here? Molarity. So what are the units on K going to be? Look at this. This is molarity per second equals K times, what does this work out to be? It works out to be molarity squared times molarity to the 0.
Which is 1.
Which is 1. So therefore, it is molarity per second, K times molarity squared.
That's just
So what do the units on K have to be? Write them down. Write them down. What are the units on K going to be in this case? Discuss with the people next to you if you need
Second
to.
times the
What is
negative
that going to be?
Yeah. Or, yeah. That's how they wrote it here.
How many molarities do I need to get rid of in this case?
1.
1. So this is going to be 1 over molarity per second. Okay? The second, I need to put a per second in there. I need to get rid of one of my factors of molarity. So sometimes they will very confusingly write like the units on K are liters per mole seconds. And you're like, where did that come from? Okay? That is molarity, which is moles per liter, flipped. That is reciprocal of molarity, liters per mole, and then the per second gets us there. Even worse, on the first problem we just did, what is the overall order of this reaction? 3. So this one, the rate again is molarity per second, and you've got K times molarity cubed. Molarity squared times molarity. Okay? So in this case, the units on K are 1 over molarity squared seconds, or sometimes, and you should write this down, okay, on your pink sheet, when we solve for K, we should put these units on it. K is going to be liters squared per mole squared seconds. And to think, just barely over a year ago, you were first learning your dimensional analysis. And now we have liters squared over mole squared seconds. Sometimes they'll write it with a negative exponent. And they'll say liters squared moles to the -2 seconds to the -1 as the units on 1.35 times 10 to the -3. You should be ready for any of those versions of the value of K. Turn the pink piece of paper over. There, the numbers are not quite so pretty. They're doable, but they're not like 1 and 4. Okay? Game on.
Just happened. I didn't do that.
Just playing with my heart.
That
Playing with you. I'll say it a loud note.
Yeah, here you go.
Wow. Frisbee extraordinary.
Thank you.
Wasn't hard enough.
Attention skills.
Dave, what's a possible range of K values?
Yeah.
They can vary enormously. They can be 10 to the third, they can be 10 to the -3rd.
And will you always end up with 0, 1, or 2? Or is it possible to have something?
They said it's possible in the textbook, but it's just so unlikely unless you're working with crazy.
As I will explain next week, it is unlikely to be fractional. They might throw it on us just to be mean, but in general, they are integer values for the exponents.
So in our lab, we can round.
Yeah.
Based on.
When we're doing big time round, none of the numbers are going to be this clean. You're going to be guessing. It's oh, that could be an 8. Like it's this data very cleaned up for this purposes. But it's your first one. Mayu, what do you want to compare? Which two reaction rows?
The first for x, the first and second.
All right, so we're going 0.25 over 0.10 to some mysterious power equals 150 over 24. Connor, what's 150 over 24 give us?
25 over 4.
Let's say it's what?
25 over 4.
Or 0.16.
What?
20.
I'm asking Connor what 150 over 24 is.
It is 6.2.
6.25. Okay. Ellie, what is 0.25 over 0.1? 2.5. So we're just going to try on our calculator various values for how does that get to there. And what do we find out it is?
2.
It's 2. Okay. X is 2. We could, if we were feeling a little shaky, like run that again. Let's see if there's another place. Oh, no, there only gave us 2 possibilities. Okay. No, I guess you could run 3 and 4 as well. You could do 0.35 over 0.10. Then the x equals 735 over 60. Let's do it just for funsies. Okay, if you haven't done it yet, this is 3.5 to what power? What's 760 divided by 60? 735 divided by 60? 12.25. Does 3.5 squared equals 12.25? Close enough? Yes. Alright, so that confirms that x equals 2. We feel good about that. It is possible to go on. They could have not given us the clean opportunity to test B. Because once you know what x is, you can use that in other problems where they don't give you a clean time when x is not changing. We know what the concentration of NO, what its power is, so we could use other problems. But they gave us something nice and clean. What did they give us, Mark Edwards? First and third. So in that case, we've got 0.5 divided by 0.2 to the y power equals 60 over 24. Henry, with 60 over 24? 2.5. What's this? 2.5. So y equals 1. Smile and nod. Easy peasy. Okay. They asked us for K here. Diego, do you have a row in particular you wanted to do? What did you do in your notes? What row did you use?
The first one.
Okay, so we're going with the first one. 0.1 squared times 0.2 the first times K equals 24 mole per second. Jack, should I ask you or should I just go on back with Mayu? Okay, Mayu, go ahead. What did you get as the K value here, sir?
1.2 times 10 to the 4th.
1.2 times 10 to the 4th. Other people are agreeing. Connor, what are the units on this K value?
It's gonna be 1 over moles squared seconds.
1 over mole squared seconds. The mole squared is, the moles is squared, the seconds is not. Molarity squared. Oakley dokley. Alright. And now they asked us to use that information in a scenario. Okay. Calculate the rate of formation of product and the rate of consumption of this when this and that are these things. So when NO is 0.5, that one was squared. BR 0.3 the first. This was, what was this again? 1.2 times 10 to the 5th? 1.2 times
10 to the 4th.
10 to the 4th. And this is going to give me the rate of formation of NOBR. Okay, because that's what our stuff was in. Okay, so we're plugging and chugging with this to find, under these conditions, what will it be?
900.
Moles per liter second.
900 molar per second, which is reasonable considering like some of the other values they gave us there. If the NOBR is 900 molar per second that is forming, okay, what is the rate for something else going to be? Look at the reaction at the top.
I know it's gonna have the same rate.
Same rate except one minor detail, maybe?
What minor?
Different unit.
Nope. Negative. Because
Negative.
that's going to be going away. Rates are always positive, so it's, that one is going to be decreasing at 900 molar per second. Like there's an implied like it's going to be going down. Sometimes they'll ask you for it, sometimes they won't. Yeah.
They say, even though they say the rate of consumption versus formation.
And maybe that's okay because they say consumption. Maybe we don't need it. Maybe I'm being picky there. Okay. What is the rate of consumption of BR2 going to be? Half. Because you can see that it's just based on the coefficients of the balanced chemical equation. For every 2 of these that go away, 1 of these go away. So this is going to be consumed at 450 molar per second, which is pretty fast if you think about
Wait,
it.
so did we decide that NO is or is not positive?
I'll say that because they say rate of consumption, the negativity is implied there. Feeling all right? You guys want to take a break now or push through and do one more needs to be done?
Push
Push
through
through,
and
do
be
one
done.
more, be done.
So here is a sample AP problem on method of initial rates. For you and the person next to you to work on together.
Okay, this is the last one's actually really good.
Yeah, sure. I'm sure about that. I'm sure it works on that.
Okay.
Okay, you don't need problem.
Should we do it on there?
Should
we do it?
Doesn't matter.
Like I woke up this morning with like some sort of serenity. I was just like going.
All results are
So we would do 0.75 over